In this video, we will be exploring the time series tool on Predictive Science's new MHDweb 2.0. This tutorial is part 5 of a 12-part series that is designed to guide users through this website's data visualization tools. If you have not done so already, it is recommended that you review part 1 of this series, which covers in greater detail this website's architecture, general visualization workflow, and the mass run database. With that being said, to get started with time series plots, navigate to the MHDweb landing page, which is predpsi.com/MHDweb2, and then click on the time series button here. Now, for the purposes of this tutorial, we'll be using a more recent Carrington run, namely Carrington rotation 2289, and I'll be selecting the thermotube. And from here, I'm going to go ahead and select the heliospheric domain, and we'll get into why I made this selection in just a little bit. So the general data fetching pipeline for the time series tools begins by fetching hourly ephemeris for a selected spacecraft, utilizing Jet Propulsion Laboratories' Horizons API, between the selected mass runs start time and end time. For each hourly timestamp within this range, the spacecraft's instrument measurements, for whatever the specified variable is, are queried from Goddard's COHOweb database. The positional data of the spacecraft trajectory is used to interpolate through the simulation's corresponding variables 3D data file and then plotted. And I have attached references to these resources in the video description below, both for the JPL Horizons API and for Goddard's COHOweb database. You can select a spacecraft from the Spacecraft dropdown in the Observation widget, which I'm going to collapse the Tool widget, and you'll see that right here from this dropdown. Currently, time series comparison supports over a dozen distinct spacecraft with missions spanning well over 60 years. There exists a number of more recent missions, including Parker Solar Probe, Solar Orbiter, Stereo A and B, as well as a number of sort of legacy missions, including Pioneer Venus, Voyager 1 and 2, Helios 1 and 2. The default comparison used is the Omni dataset, which is a multi-source collection of near-Earth magnetic field and plasma data readings, which has near-contiguous heliospheric data availability. One consideration when plotting with the time series tool is that spacecraft trajectories must intersect with a mass runs domain. Most spacecraft trajectories are constrained to the heliosphere, with the notable exception being Parker Solar Probe, which dips below the coronal boundary during its perihelion encounters. But as such, certain mass runs that only have a coronal solution are naturally not going to be viable candidates for comparison. Similarly, certain deep space missions might have some intersection with the heliospheric domain, generally towards the beginning of their mission, but eventually wind up well beyond the heliosphere. So think Voyager 1 and 2. So just keep this in mind when presented with a validation error on the plot. And going back to the beginning of this tutorial, that is why I changed the domain from coronal to heliospheric, because if I select the coronal domain here, you will see the validation error that spacecraft positions do not intersect this domain, and that's because I am currently considering the Omni data source, which is near-Earth instrument readings. So I'm going to go ahead and change that back to the heliospheric domain. As mentioned in part 1 of this series, you can use the mass run database interface to filter by spacecraft data availability as well as domain availability. And just to review that functionality quickly, we go to the simulation database interface. And from here, in these dropdowns here, you can select by spacecraft data range. So for example, I'll select the time range start for Parker Solar Probe and the time range end for Parker Solar Probe. Now this corresponds to the data that is available through the COHOweb database, even though this is an ongoing mission. Now you can see by inputting this data availability lower bound and upper bound, the number of mass runs has dropped from nearly 2,000 to 371. From here, if we want to select just runs that have a heliospheric solution, in this drop-down here you can select heliospheric, and you can see that number drop from 371 to 366. With that being said, I'm going to go ahead and close this and return back to our Carrington rotation 2289 Thermo 2 run. The other consideration to keep in mind is that when visualizing a time-dependent simulation, some of which contain hundreds of states, each hourly timestamp generally maps to a particular state, and as such, this can involve a tremendous amount of I/O, reading and interpolating hundreds of files. As such, these plots may be a bit more sluggish in terms of responsiveness, although we have done our best to make this as performant as possible. By default, the time series plot uses the entire model run range as its x-axis or time axis limits. However, when considering runs that have a prohibitively wide time range, the minimum and maximum time axis limits are constrained to plus or minus 5 Carrington rotations from the time of interest that has been selected. In practice, this limitation, this plus or minus 5 Carrington rotation, is only really seen when examining what we call collection runs, which are covered in greater detail in part 1 of this series. These are pseudo time-dependent runs where each state corresponds to a unique Carrington rotation and can span decades. So just to illustrate this, I'm going to select the Simulation Database interface, filter by collection run, and these top 3 here are aggregate runs of all of our Thermo 2, Thermo 1, and Poly Carrington rotation runs. So let's say I select Thermo 2, and I'm going to select the heliospheric domain since I'm considering omnidata. And the result is a aggregate run which sort of acts like a time-dependent run. So instead of having a single steady state, we have a state corresponding to each Carrington rotation here. So previously we were looking at Carrington rotation 2289. So that'll move our time of interest over there. But now we have a much wider range that we can consider on our time series plot. So as I previously mentioned, what's happening here is we're taking the time of interest and going behind 5 Carrington rotations and ahead 5 Carrington rotations, taking that collection of states, finding the ephemeris that lie within those states, and then interpolating through each one of those files the corresponding positional data, and then plotting it here on this time series. So with that being said, I'm going to return to the original run that we were looking at, which is just the steady state run for Carrington rotation 2289, the Thermo 2 version of that, and selecting the heliosphere. As I mentioned before, the default value is going to be the Omni dataset. But let's say for the purposes of this tutorial, I want to examine a few different spacecraft. And so I can select the Parker Solar Probe mission by selecting it from this drop down here. And one thing to note before moving on is that you can change various aesthetic components as with many of the other widgets on this drop down here. So this will dictate line color, the symbols where you're interpolating at, line width, and line style. So let's say instead of wanting an orange line color, I will select something perhaps green here. There we go. So one thing that becomes immediately apparent with this plot is that there's a gap in the Thermo 2 data between here and here. The Carrington rotation that we've selected happens to have a Parker encounter where it dips below the coronal boundary. So for spacecraft positions that lie below 30 solar radii, we won't have data for the Thermo 2 run. However, if we wanted to see the data values that exist within there, we can select within our domain dropdown the coronal solution. Once again, we'll go back to the heliospheric domain. Now the next component of this tool that we'll cover is the data widget up in the upper left-hand corner. For time series plots, this widget is responsible for determining if and how the data is smoothed, as well as the usual stylistic manipulations. If the Smooth Data button is toggled off, you'll be presented with the raw data that is pulled from COHOweb. And then again, if this option is toggled on, you'll have the ability to smooth the curve using a boxcar averager. You can specify the rolling average window between 1 hour, which would effectively be raw data, and 24 hours. So by default, this smoothing excludes missing values. However, that can be toggled on or off. So you can see in this plot there's some missing values that are sort of towards the tail end of this plot. And by toggling the include missing values, this curve now becomes more continuous in this area. And effectively what that is doing is for those values where there was no data readings from the instrument, the average value calculated from that boxcar window will be supplied at those spots. Alternatively, you can use linear interpolation to supply those missing values by toggling this value on or off. So just a couple more things to note within this data widget. Within the style customization subwidget, you can also specify whether or not you simply want to view the signed value, which is the default for the vector components of the magnetic field, which is namely to show the field polarity. And you can also show fill color as well by toggling this on. And showing this fill color can really highlight, to what extent the time series plots converge or diverge, how similar they are. Now, before moving on, I'm going to collapse some of these menus here. I'm also going to change the data smoothing window to a 12-hour window here. And next we're going to take a look at the point widget, which allows you to query the plot at a specific time and view the corresponding values for the mass run and the spacecraft instrument data. So to do that, you're going to select the query time, and you'll see some lines and text that have now popped up onto the time series comparisons. So in this field, I can specify the time that I would like to query. So I'm going to query something towards the beginning of this time series comparisons. And you'll see that in the upper left-hand corner, you'll be presented with the ephemeris, and in the upper right-hand corner, the values are provided. So you can see here that on the 24th of September, Parker Solar Probe was at 62.1 solar radii. And as I step through this time series comparison, you can see Parker Solar Probe slowly approaching the coronal boundary as it reaches its encounter event. Another thing to note is that the ephemeris is queried at an hourly cadence. So if you supply a time of interest that lies somewhere in between hours, it'll simply round to the nearest hour, as you can see here. And lastly, we will take a look at the view widget. And this allows you to specify a particular subset of the time series plot to effectively zoom in on. When setting your axis limits, keep in mind that if your x-axis or time range does not include the specified time of interest, the corresponding axis limit will snap to that value. So currently my time of interest is the default value that is provided, which is the midpoint of the run time range. But let's say my time of interest was October 7th. And let's say I put my ending time range at October 1st. You'll see this validation error beneath it that says the time of interest is outside the selected time range. And if you look at the modified value or the plot itself, you'll see that it is snapped to October 7th. So for our purposes, I'm going to select a time of interest that is within that axis range. So let's do September 24th. And now you'll see that the axis limits are from September 19th to October 1st. And I can adjust that from here. So let's say I put in September 22nd. And you'll see that the time series plot is zooming in on this time range here. As with all of the plots on MHDwebX, you're able to download both the plot image right here, as well as the underlying data that is used to generate the plot. So for time series comparisons, you have the option to download either a fixed width ASCII file or an ECSV file. So ECSV, which stands for Enhanced Character Separated Values, was created by the developers of Astropy as a human-readable file format which can be read into a Python script to produce an Astropy table. It's similar to a CSV file, but provides additional metadata about the data contained in the file, and when read using Astropy will yield a table with native Python data types and relevant utants, coordinate systems, and timescales. And you can see a link to the Astropy package documentation in the video description below, along with those links to the JPL Horizons API and COHOweb database. And with that being said, that concludes our overview of the time series tool on Predictive Science's MHDweb 2.0. The next video in this series will go on to explore the spacecraft mapping tool. If you have any questions, comments, or concerns, please leave a comment below. And thanks for watching.